Test, test. Oh. Does it work now? No? Okay. Probably we should test it and again. Not now? Okay, perfect. Thanks a lot. So probably I should also. All right. Okay, now it should work. So. All right, okay. So I will be quickly rushing through my intro slides. So welcome again to the 4th workshop on open source design automation. So I'm using everything open source on my laptop. So sometimes it doesn't always work plug and play. So this was a live demonstration. So thank you for your patience. Okay. So, first of all, as you might have noticed, we are on YouTube because we want to share our discussions and insights and contents with the rest of the world. So you don't have to be here, and it's conserved somehow also for future generations and for ourselves as well. So yeah, just wanted to say clearly, so if you mind asking a question but don't like to be on YouTube, probably consider asking your neighbor if he or she would like to ask the question. Otherwise, if you ask a question, we may assume your consent to be on YouTube. So I hope this assumption is also valid for you. And we stitched together those microphones. One is for the room. Hello, hello. Oh, I have to switch it on. Hello, hello. No? Yes? Test, test. Okay, so one is for the room, one is for the stream. So the one with the OSDA logo is for the stream. And I would kindly like to ask you to ideally speak into both microphones so everybody around the globe can hear you once you ask your question. Thank you very much in advance. Okay, so, yes. So if you want a link to the YouTube stream, you can find it here. You may also find it on our website, which you may access through this link or this QR code. It's visible throughout my further presentation. All right. So yeah, it's now it's time for me to say thank you to all those people who made it possible to do this workshop again. So, of course, first of all the executives, the organizing committee, the technical program committee who made very good suggestions who to invite, did a lot of work in reviewing papers, all the authors who made their effort in preparing a manuscript and submitting it to OSDA, and of course the speakers who didn't hesitate to come here, although crossing several time zones. So thank you for suffering for us, for jet lag. So thank you very much. Also, so it's very nice to see this full room here. Thank you to our audience. So like last year, OSDA is the workshop with the most registrations. So thank you for that. Thank you for your interest. So it clearly shows that there is demand and there is high interest in open source design automation within this community. So we are happy to contribute and cater for these needs. So yeah. Last but not least, I would like to say thank you to the Date Conference organization for putting up this nice conference and for the great support they provided whenever we had questions. And yeah, so a little bit ahead of time, so quickly rush through the workshop program. Yeah, so it's available at this link or through this QR code. So we made last minute changes to the program because some speakers were not able to come, so please check out. Yeah, in case you are interested for follow-ups and for infos on possible next edition of OSDA, please don't hesitate to subscribe to our newsletter or follow us on our social media accounts. We are going to have talks between 2 and 4. Then there is 1 hour poster session, including the coffee break. And then we return to talks again at 5 p.m. Yes, so half an hour is a little bit short for discussing all the posters and for side talks, so we decided to extend the poster session a little bit. Yeah, so this year it's the first time that OSDA is split into 2 parts. The first one is here, the physical part, where we can interact with the rest of Date Conference and with each other. It's always a little bit more compelling to talk face to face, have fun together. With 6 invited speakers, 1 demo presentation, and 9 posters this year. And the virtual part, which enables participants of these workshops from abroad who are not able to come here and to spend a certain amount of money to present their open source work, we decided to set up a virtual part as well, which will take place in 3 weeks in cyberspace. You can find the link here in this QR code. And yeah, so we will provide these slides so you don't have to write them down quickly. So yeah, and there are 5 registered presentations so far. I brought some stickers actually, so if you're interested, please approach me during the coffee break. And yeah, so we have 9 posters today. You will find them in the back of the room. And yeah, I will just quickly click through them so you may discover them by yourself in the break later. So it's time for me again to wish you a nice workshop, and I would like to introduce our first speaker, which is Luca Canoni. Luca Canoni is professor at Columbia University, and today he will present an SOC framework, ESP, but I think he's the one who will tell you right now. So welcome our speaker. You're already connected? Oh, yeah. Perfect.
We want to be like this, I guess. Okay. Right, okay. That's cool. Well, thank you very much, Christian, for... Can you hear me? Yeah. Usually I have a fairly loud voice. Thank you very much, Christian, for the invitation and the committee for organizing this workshop. I'm excited to be here. My name is Luca Carloni. I've been with Columbia University for the past 20 years. And today I'll tell you about ESP, which is a project that is really the result of 10 years plus of research that became an open source project about 4.5 years ago or so. And ESP is an open source platform for collaborative design of a heterogeneous system on chip. So let me start with a little bit of motivation. This is really motivation for the research that my collaborators and I have been doing at Columbia for even more than 10 years. So we actually always focus on heterogeneous computing. We define heterogeneous computing as computing about systems which are made of components that have different nature, heterogeneous. So not just processor, but also GPUs, and particularly specialized hardware accelerators that, as you see, are one of the emphases of our research, as well as memory hierarchies, peripherals, and so forth. And we have started working on this type of systems many years ago, and you may have noticed that the migration towards heterogeneous system on chip, in particular architectures, has been accelerated almost across all computing domains, from IoT devices all the way to data centers and even supercomputers. And so professors have always to look ahead. So if I look ahead 10 years from now, I'm going to say that in a given year, let's say 2034, the set of a heterogeneous system on chip in production across all possible markets and computing domain, that set itself will be heterogeneous. What I mean with that is that I don't expect a single system on chip architecture and software stack to be dominant across all markets and computing domains. Quite the opposite. I think that we will have a rich variety which offers a lot of opportunities for research, for innovation, and this should be taken, I think, as good news, particularly in the younger generations among us. So there is a lot of opportunity to contribute. Now, I don't have the time to explain why heterogeneous computing has emerged. Essentially, there are all those technology trends, particularly the slowdowns of Moore's law, and particularly the end of the NAR scaling, that make the need of using transistor to create specialized compared to a general purpose CPU. And fixed function accelerators are even more specialized. Why? Because they provide better performance and energy efficiency for a key computational task compared to executing things in software. And however, heterogeneity brings challenges, obvious challenges. They are inherent to the fact that the system is made of parts which have different nature. At the same time, you have diminishing regularity in the system, all the way to the chip layout. This makes things like design, validation, verification more complex. At runtime, you have more complex hardware-software interaction. You manage shared resources, for instance, the power envelope or the access to external memory across components which have different needs. This makes things more complex. And in fact, this has been noted. With each system-on-chip generation in a given product line, the addition of new capabilities is increasingly limited by engineering effort and team sizes. So the biggest challenges are, in my opinion, and will increasingly be, to be found with the community. The goal, I guess, is to try to have at least some of the success the open source software has had over the last 30, 40 years plus. From some research labs, we have noticed years ago that many of these projects focus particularly on the development of components, which is very important, like an open source processor, an open source GPU, an open source accelerator, maybe an open source interconnect. But this leaves open a critical challenge. We can target application domain by efficiently reusing and combining a variety of independently developed, heterogeneous, open source hardware components, especially if these components are designed by separate organizations for separate purposes. And this is really the challenge that we have been tackling with my platform. Now, platform is one of those buzzwords in our field that has multiple definitions. So our definition is that a platform is a combination of an architecture intended as a computer. An SoC architecture enables design reuse when it simplifies the integration of many components that are independently developed. An SoC methodology enables design collaboration when it allows. So you need an effective combination of the architecture and methodology in order to have a platform that maximizes the potential of open source hardware. This is one possibility, and so in fact in the website you can find not only the link to GitHub with the code, but also the link to a YouTube channel, as well as quite a bit of documentation, to the extent that you can expect documentation from an academic project, but there are hands-on tutorials, similar stuff. As you may have noticed on the latest post, these are really latest. We have a release made really last week. We try to do a couple of releases, major releases per year. And particularly, and I'm going to talk about that in the last part of my talk, we have that last month we presented a system on chip designed with the ESP platform, both the architecture and methodology, at ISSCC in San Francisco. And this is a major milestone for the ESP project. Is a chip that you'll see for complexity. I talk instruction on 3 parts, which I'll try to go over in the remaining time. First, I'll tell you a little bit more about the architecture. Then I'll tell you a little bit more about methodology. Architecture and methodology are really developed together. One is companion to the other. And then I'll tell you about how we can use the platform, so the two, to do scalable, collaborative system on chip design with a very concrete example. In fact, a couple of them. So the architecture. An SoC, this is an example, this is a cartoon of one possible instance of an ESP system. It's a tile-based architecture. You see an example with 16 tiles organized in a 4x4 matrix. The matrix could have a different structure, 6x4, 8x8. In the tiles, you have, in this example, that the colors denote tiles with really a different nature. There are more than given the time, and because they are the most important, the ones that have been around since the beginning of ESP. One is the processor tile, the other one is the memory tile, and the third is the accelerator tile. Now, in the complex, ESP as an architecture implements a system which is distributed in the context of a single chip, where communication is as important as computation, so in that context. Scalable, modular, and heterogeneous, giving processor and accelerator similar weight in the SoC, so they are given really the same importance. This maybe distinguishes us from some other academic platforms where we think the emphasis is particularly given on the processor. For us, the accelerator, which are, as you'll see, loosely coupled and designed. So processor develop like change things. RISC-V and Spark are 2 very different instruction set architecture. In fact, they have different endianness. This processor come with a level 1 private. We extended, and you'll see on the right-hand side, within a socket. This is the socket that embraces the component and creates the tile. So the tile is a combination of a component and a socket around it. So we extended with a socket that in this particular case provides a level 2 cache of configurable size, and speaking through the network on chip that connects every tile in ESP. You see those NOC routers, so a 2D mesh network on chip. I don't have the time to go in much details, but it's a 2D mesh network on chip, multi-plane, so you can configure how many networks, different distinct networks you can have in your system. Typically nowadays we do system with 6 planes. So the socket, in this case, instance a level 2 private cache, and connects the cache, the processor through the cache, through the rest of the system, through the network on chip, and also implements a MASI protocol, which is a cache coherency protocol on top of the distributed network on chip. Another very important tile is the memory tile. You can have more than one memory tile. You can configure a system with more than one. One single memory tile typically gives you the interface to off-chip memory, to DRAM, so you can have the memory controller instance there, or some other I/O that allows you to speak with external memory. And typically you also have the last level cache with the directory, distributed approach based on the MASI protocol. If you have 2 or 4 memory tiles, the ESP methodology allows you to automatically partition the cache and partition the directory, so that you don't have to be concerned about that. It also supports DMA channels to bypass the cache, as you'll see a bit later. Then the third type of tile, which is very important, is the accelerator tile. So, of course, the accelerator can come very different, for very different purposes, and so really here you have to distinguish at the bottom the green part, which is where there is the data path the accelerator, together with the PLM. PLM stands for private local memory, so it's different from a cache. Those of you who design accelerator know that in order to have a very high parallelism, you need to typically create a multi-bank, multi-ported local memory there, typically done in SRAM or VRAM, depending whether you do a chip or an FPGA. The socket, in the case of the accelerator, extends the accelerator with interface to the network on chip, and engines like DMA engines something equivalent to TLB, if you want the accelerator coherent ability to have the equivalent of a level 2 cache locally, interrupt request mechanism, and particularly configuration register. The PLM is not memory mapped, it's private to the accelerator. The configuration registers are memory mapped. So this shows you already an important characteristic, which I'll stress with this slide. The designer of the accelerator really can count on the fact that the socket provides these capabilities, DMA, address translation, interrupt request, and other services I'll mention in a second. So therefore, because these are provided, the designer can really focus on the design of the accelerator, which is where most of the innovation in domain-specific SoC goes. So we will see in the part on the methodology that we support various, within the same methodology, various design flows to design accelerators. What this slide shows you, in contrast, is that you can also take accelerator, develop completely independently from ESP, particularly if those accelerators speak some of standard buses like the one mentioned in the slide. So we call them third-party accelerator. For us, it was a very important moment when a few years ago the NVIDIA company released the NVIDIA LA in open source, and because it gives us confirmation that many things that we had decided when we developed ESP, including focusing on loosely coupled accelerator, creating a socket in a modular way, really was compatible with some of what we thought was excellent research in accelerator design. So there is also the equivalent, if you want to call it, of a software socket. So far I focus on the hardware. The software socket really is more like the support that the ESP provides is to invoke a hardware accelerator. Now, how you invoke an hardware accelerator? When an hardware accelerator is a loosely coupled accelerator designed independently from the processor, and ESP, the accelerator are like that, to be very concrete, I could take an ESP system, configure it for a RISC-V processor, have many different accelerators, and then at the last minute switch the processor from RISC-V to Leon 3. I don't have to change anything, I just have to recompile the code. So these accelerators, they are loosely coupled, execute tasks which are coarse-grained, typically accessing very large amount of memory, typically in DMA, although we support also some type of coherency access from DRAM. So when you access a lot of memory, really this accelerator executes for millions of clock cycles. Of course, this is still better than executing the same task in software, taking maybe hundreds of millions of clock cycles. So how do you invoke this accelerator? You invoke them to a device driver. A device driver becomes a very little overhead in the context of such a coarse-grained task. So you have system calls, and really there is a very lightweight API. You see the three main primitives to allocate memory, to free memory, and to invoke a particular accelerator as if we were invoking a software function. In fact, typically when we develop accelerator, we first have a version in software where we invoke a software function, and then with the code we just switch between the two. And this is a way also to validate. This is how we teach accelerator design to our students. So the socket implements also the interface to the network on chip, and support services. I already mentioned some of the services. Depending on the particular tile, you can have different services. This is really a key approach in ESP. You want to decouple the design of the component from the design of the system, and you want to make sure that certain problems that are very important in system integration, for example, managing coherency, supporting DMA, supporting interrupt, also lower level problems, also like, for instance, supporting dynamic voltage frequency scaling at the level of tiles. These don't have to be reinvented all the time. You don't want to reinvent the wheel on this stuff. You want to focus on what is the emphasis, what is the key to innovation, which is which accelerator you design, which matrix you want to have in your system, which tiles, number, mix, and so forth. So we continuously develop new services. We call them platform services that we, and different types of tiles have different type of services, although some are shared, like dynamic voltage frequency scaling, and the circuitry to support that is available. Typically, you can have it for every tile. Okay, I'm going fast because of the interest of time, so now I'm switching to the methodology. So the ESP methodology, this is the vision. Eventually, we will love that domain-specific application developers who know everything about their application, work with architect to decide what goes in software, goes in hardware, can design SoC. Of course, this is a long-term vision. What you can do nowadays? Nowadays, you can develop components and keep enriching the library of both the hardware library of IPs and software library that you can use in an ESP system. If we focus on accelerator as an example, you can develop these components with a variety of languages. I told you that this is a key characteristic of ESP. We don't demand one particular language. So you can work at the RTL level and use one of the classic or innovative languages that there are for RTL design. Or you can do, as we recommend, particularly for accelerator, work at a higher level of abstraction. Use C, C++, System C, and use high-level synthesis. And we support all the high-level synthesis commercial tools, and we are about to support also the open source tools. Of course, in order to build this system, we have to rely on commercial tools, as you'll see, which is the type of chip that we build. But we are also open to try to add design flows that are based on open source tools. An example of a combination of the two is what is shown at the top. This is something that where we rely on another open source project to which we contribute, but we don't lead, called HLS for ML. Is a great compiler that allows you to take specification of neural networks in all the typical frameworks for neural networks and produce synthesizable C, C++ that then you can use to create hardware, and we have integrated that inside ESP. So then from that you have the component, and people can develop and enrich the library. The architect can decide which component to use, which new component to develop and contribute to the library. And then you can do the configuration of your tile matrix, decide the number of tiles, decide the mix of tiles. And then for many years, quickly, we went through rapid prototyping on FPGA. More recently, as you'll see in the third part of my talk, we are very happy that we have demonstrated some of this agile design approach with actual chip designs and not just SoC emulation of system on chip. So many aspects of the methodology are either automated or interactive, partially automated. There are aspects that are manual. So for instance, in the accelerator flow, the design of the accelerator remains a manual effort, and we think that actually, at least for the foreseeable future, is one of the key in expecting the contribution of the engineering team that decide really how to optimize this accelerator. But we try to make things around that as automatic as possible, and quite a bit the SoC flow, as you'll see in a slide in a second, as a graphical interface that guides you with a lot of automated steps. So design of accelerator is a key. We have been teaching at Columbia accelerator design to undergraduate students now for several years, and we emphasize particularly on using high-level synthesis. So you have a programming view where you design this hardware accelerator using C, C++, System C, and then using high-level synthesis, you can, using the knobs that high-level synthesis gives you, loop pipelining, loop unrolling, parallelization, you can, from one single specification, produce many different implementations, some of which will be Pareto optimal with respect to your objective function. Typically in hardware, objective function are a function of performance, assuming that I mean latency in that slide, so the lower the better, the closer to the origin, the faster, and a function of cost, area, power combination. And so you have these Pareto curves, and of course you want to have a rich Pareto curve, which is, are those designs that are optimal in this bi-objective optimization setting. But when you have developed one particular version of your accelerator, maybe you still don't hit the exact performance and area figures that you want to meet. So then, certainly you need design effort. So you go back to your C, C++, System C, and you try to change the architecture. But again, you rely on high-level synthesis to obtain many different implementations from a single specification. And this is what we really teach to try to make design for usability. Why? Because if you look at the projection on the two axes of a Pareto curve, the bigger is the segment that gets projected on the axis, the higher is the trade-off that you can play with. You can have the same accelerator implemented with quite a bit of area for very high performance, or with much less area and power for lower performance. And if you have all these capabilities in your library, then different architects, whether they're doing IoT or high performance design, can choose different accelerators. And one key point is that the socket that I told you before allows you to absorb into the system the differences, microarchitectural difference of the accelerator without having to redesign anything. This goes back to stuff that I've done during my PhD, which is the concept of latency-sensitive design, where at the time I was targeting the problem of long delay in communication between components on RTL design, so not with high-level synthesis, and I created this theory of latency-sensitive design that tells you that if you take a piece of RTL and you decompose it in components that can be stalled through clock gating, then it's always possible for you to create a shell while knowing only the input and the output without knowing what the component does. And this shell, which is shown there around the stallable core, is really a combination of queues and some control logic for clock gating that allows you to make sure that then you can pipeline the wires and even if you change the latency on wires, even on feedback loop or very complex design, you don't have to redesign the core. You are guaranteed to have a correct design. Your mileage for performance may vary depending on many system level considerations, but the correct and functional correctness interpreted as latency equivalent design is given by construction. So these are the same principles that we use in the socket and allows us to take, for example, an accelerator and when we have already designed the complete SoC and changes implementation, take an accelerator with higher parallels or lower parallels that takes a different number of clock cycles to execute a task and not having to redesign anything because it communicates and gets integrated with the system. So this is very important for design reuse and for collaborative design. So this is just a quick demo of the ESP graphical user interface. You start, you design which kind of matrix of tiles you want. For each tile, you decide whether it's a processor, a memory, an accelerator. If it's an accelerator, you go into the library, you decide which kind of particular implementation on your Pareto curve you want. You can change it and then do quick prototyping with FPGA and see the effect of your change. You can also do other things, decide coherency. You can decide to add monitors that you typically monitors, we put them in the socket and allow you to do more diagnostic and understand better how your system operates. Now, in the remaining time, very quickly. So, for many years, we focus on developing SoC on FPGA, so emulating essentially SoC FPGA, although sometimes we implemented that, which is, and we developed quite complex SoC. This was presented at DAC almost 10 years ago. This is for a computer vision application, and what you see here is a live demo at the time where the heat map on the right-hand side tells you where the traffic is going, while you have this, if I remember, 16 accelerators. There is one processor, a Leon 3 processor, an IO tile. In this particular picture, there are two memory tiles at the two opposite corners. You could just say one memory tile or two memory tiles, and of course this increases the bandwidth of chip. And as if you double the memory tiles, or you put 4 memory tiles, and this reduces the congestion in the NOC, and you can experiment through rapid prototype. So for many years we focused on FPGA. We had a fairly robust flow to implement a complex SoC on FPGA. But then, of course, our goal has always been to demonstrate this with ASICs. And now I'm very happy to tell you that we have presented a month ago, as I mentioned, at the SSCC, this system on chip. This is designed in 12 nanometer FinFET, which is a fairly advanced technology for an academic chip. It's a 64 millimeter square SoC with 35 clock domains, 23 power domains. So we have quite a bit of scalability at runtime of deciding how each tile operates in terms of frequency and voltage. 8.4 megabit of on-chip SRAM, 34 tiles connected by a 6-plane 2D mesh network on chip that provides 74 terabit per second. It has 23 accelerators of 14 different types. 10 accelerators compose a cluster, which may be seen with that red perimeter, which demonstrates a very novel distributed hardware power management scheme that is an algorithm contributed by our collaborators at IBM. This was designed by a small team of mostly PhD students. We are talking about 8 people, led by PhD students. There are also one postdoc, a couple of industrial research in the span of 3 months using the ESP methodology. The chip came back last July, it arrived on Wednesday. By Friday, it was built in Linux SMP, invoking the accelerators. So, as sources of IP, how are we doing in time?
It's
fine.
If you're close to the conclusion.
I'm relatively close to the conclusion. Okay, I'll try to go fast. So, thanks for your patience. So, this slide just tells you that components come from very different groups, and this is the idea of collaborative IP reuse. And they have been integrated with the ESP methodology and the ESP network on chip. Some of these components, for instance, the accelerators designed by hardware, were designed completely independently from ESP. NVIDIA Lake was designed completely independently from ESP. This was not really the first chip. We actually presented a chip a couple of years ago, which was like some sort of, in jargon, a pipe cleaner. You can see that we actually reused the same board at the time that we were going to do for the big chip. So this is a smaller version, just 4x4 tiles. Why do I bring it up? Well, to show that, of course, the epoch 1 is much more complex than epoch 0 along many different metrics. Number of accelerator, number of tiles, clock domain, power domains, and so forth. And it has been designed in actually less time. Okay, of course, we knew by then the technology was the same technology, but more or less by the same people. So this is a claim of the scalable approach to manage the complexity of SoC design. So, Before I give you my conclusion, I want to advertise another workshop. This is related to ESP, but it's an effort that I'm doing together with several collaborators. This is the third edition of the OSCAR workshop, which is the open source computer architecture research that we do together with ISCA. And so the call for abstract, which are really for just presentation and poster, you can find it at that website. It has a deadline at the end of April. And so this, besides contributing to the community with ESP, we think it's very important that we foster a community that is interested in doing open source computer architecture in the broad sense, research, and contribute components, use components, and evaluate. So, in conclusion, we contribute ESP to the open source hardware community in order to support the realization of more scalable architecture for system on chip that integrate more heterogeneous components thanks to a more flexible design methodology which accommodates different specification languages and different design flows. ESP was conceived as a heterogeneous integration platform from the start and tested through years of teaching at Columbia University. We invite you to use ESP for your projects and to contribute to ESP. Thank you very much for your attention.
Thank you very much, Luca. Are there questions? One or two quick questions? Yes.
Thanks, Luca. Do you always have to have one processor to invoke the accelerators through your API? That's my first question. The second question is, does the NOC always have to be a 2D mesh or other topologies built in and allowed?
Thank you, Jason. Two excellent questions. So, first of all, the first question is, does an SoC always have to have a processor? Well, if you want to boot the OS, yes. Now, ESP is used as we speak by, although we focus primarily on high-performance SoCs when we develop ESP, with the idea of booting Linux and operating system. In fact, we want to boot even Linux SMP. But now we have people that are interested in using ESP for a simpler system, so which probably don't boot the OS and maybe not even an RTOS. Probably they do bare metal. In those cases, you may use a very simple processor. It may still be helpful. I guess you could imagine to use ESP without a processor. That would require a little bit of extra effort because some of the things that we provide in order to easily integrate accelerator, whether bare metal or not bare metal, would have probably to be adjusted. With respect to the network on chip, I've done quite a bit of, as you know, quite a bit of research on network on chip, and there has been an amazing community over the last 25 years doing research on a variety of network on chip. In the end, for ESP, we made a very important decision, which is that we use something relatively simple, a 2D mesh, no virtual channel, but multiple plane. So this is why, for instance, cache coherency, to guarantee absence of protocol deadlock, we have to use 3 planes, because we don't have virtual channels. And then also in terms of protocol, flow control, and those fairly simple stuff. Why? Because it has to support a big variety of configurations of the systems as well as the network on chip. You can have different parallelism on different planes. You can have different number of planes. You can have, so there are various things that for which we really want the simplicity and robustness. The network on chip is perhaps the single most important element of SoC. It's like so often I say it's like the nervous system of the SoC, like the backbone. Now, having said that, the design of the network on chip is decoupled from the design of the processor and the design of the accelerator. So if somebody wants to design a different network on chip for ESP with a different topology, that would be a fantastic contribution, and we would be happy to accommodate. Thanks a lot. Oh,
Thank you for contributing to this workshop.
Oh, I love this.
You know them, yeah?
I know, this is Mozart.
Yes, Mozartkugeln, Mozart spears.
Thank you, appreciate it.
Thank you. All right, so it's my pleasure to introduce our next speaker. Jean-Paul Chaput holds a master's degree in microelectronics and software engineering. Joint engineer in the analog technologies, in particular in chain infrastructure. He's now a key contributor in extending Alliance Coriolis to the analog mixed signal integration for nanometric CMOS technology. And he is fully committed to the open source hardware approach. So welcome, Jean-Paul.
Thank you, Christian, and thank you all to attending this forum. Today I will talk about a very specific problem that I did encounter in the building of the detailed router of the Coriolis toolchain. It's a very specific problem. So, oops, one slide at a time, it's better. So, to start with an analogy, the detailed router in a toolchain, in a layout toolchain, is the tool which is in task to make the layout that you will send to the foundry. In order to make an analogy for people who are not accustomed to making chips, imagine a compiler, I mean a program. You are writing source code and you want to transform that source code into a machine code that you can then run on a computer. To do that, you use a compiler, like GCC, for example. But how do you know that GCC is really compiling the right code? That the source code that you have is the code, is corresponding to the machine code that has been generated. In fact, you trust GCC. You said, okay, I will run GCC and I expect GCC to generate the right code of times, and all with detailed router. Detailed router make a similar operation. That is, it takes a reference description of your design and it describe in your netlist, typically. So this is my problem as the designer of the detailed router is to ensure and to debug the detailed router, to ensure that when someone runs the detailed router, the layout that will be generated is correct. And in fact, it's slightly different in our case, is that I want either the router to tell me, okay, I did succeed, or no, I do fail. But what I do not want is that the router tells me, yes, I did succeed, but there is an error. Typically, a short circuit, the layout is bad in some ways. And I have to debug that. So in the context of Coriolis, I have to make that, I have to develop tools to ensure, to make the checking. Because those tools are usually not very, there are not many of them, and they are not very easy to use. So here, on this slide, I detail what we need to do when we check a layout generated by a router. So there is two kinds of checking. You have the first one, which is the DRC, design rule checking, and it's a very important test which tells you that at least your layout can go to the foundry. That is, there is no obvious errors. That is, it's not a total mess of rectangles. So at least it's a basic, it's a very complex verification, but still it's the first one. The second one, which is more complex, is the LVS. The basic work of a router is to transform a netlist, which is a graph, into a set of rectangles. And you want the set of rectangles to represent the graph that you describe. So how do you do that? You perform what we call usually a LVS, layout versus schematic. So that means that you have the schematic, the netlist, which is your specification, and on the other hand, you have the extracted netlist, which is the reflection of what the layout is. So there is, in fact, in this operation, in this step of the design process, there is two operations, which is the LVS itself, but before the LVS itself, you need to have an extractor. The extractor is the tool which reads the layout, the set of rectangles, the huge set of rectangles, and generates a graph, which should be the graph representing the netlist. And usually, when we talk about LVS, we kind of forgot the extractor step. But the extractor step is a very, very important tool, because it's extremely complex. It has to process a huge amount of rectangles. It's computationally intensive, and it's prone to error also. So this slide is just the flow showing you those two steps. We are going to see how we did implement that in Coriolis. So some generality about the extractor and LS using by Coriolis. First, the algorithm is not mine. The algorithm was made by Christian Masson, which is an engineer at Bull, which was formerly C2I Honeywell Bull, then now Atos. Maybe it's a company, a French company, French computer maker company, that slightly shifted from computer making to IT. But okay. The second point is that the kind of extractor that we want to realize is not any kind of extractor, because when you talk about extracting a layout, you can talk about many different things. For example, the one we are talking about here is only a gate level extractor, meaning that we don't extract down to the transistor level. We cannot, because extracting the transistor is in itself a very complex task, because you need to recognize very specific patterns in the layout that makes a transistor. For example, as a basic thing is when you have the intersection between three layers, like a diffusion layer, an active layer, and a gate layer. Then you have a transistor. So it's extremely complex. So, and for the router, it's not the point, because my point is to check the router, and the router doesn't make transistor. It just connects gates. The second thing that this extractor does not do is that it does not make parasitic extraction. For example, if you want to check the frequency at which your chip will run, you will need to have the parasitics, which means parasitic resistance, resistors, capacitors, and all other kind of electrical parasitics that you can think of when you are doing that. So it is not that. It just generate a graph by seeing what's connected to what, and that's it. But that's one big thing. One main characteristic of this algorithm, this specific algorithm, is that is you got instance with layout in it, and if you want to make an extraction, the first, and then you have to process them flat. So this algorithm do not do that. In fact, it still performs a flattens, as we will see, but a local one, a very local one, and so we save data and speed. The second point interesting in this algorithm is integrated inside Coriolis, so we do not have a loss of information. What I do mean is that usually extractors are separated. In the process of processing the layout, you lose the netlist information. That is, you get your GDS file or your OASIS file, but in fact, you get netlist without understanding what it is. The origin to perform the extraction. And finally, one big problem with the extractors are the error message. Again, if you have made a program with template in C++ and you make an error inside the C++ template, usually the error message is quite long, but it's usually extremely long problem with the extract. It's maybe difficult and so on. So as I said, this tool do not perform a full flatten. So the first step in this tool is that instead of doing the intersection between each rectangle 2 by 2, and then you rebuild the patterns, what we perform is we use a sweep outline red area, and you action between the rectangle in that area only, which means that you don't have to fully flatten the design. Only a tiny strip of rectangles across the design. Okay, we don't flatten the whole design. In fact, they make little window. They cut their design in rectangular windows, and they flatten only in those windows. But the same way, you still win. You can parallelize things and make multiple windows. So it is not implemented yet, but it can be done. So intrinsically, that's the right one. So now, how the transhierarchical flatten is done? As I said, I do not fully flatten. So what you have on the left side of the screen is, I don't know, is the mouse running? Okay, very good. So you have model 2 here and the instance B of model. For example, one piece of metal, the virtually flattened layout. So you have the first one here, and you have the second one here. So we create temporarily, on a transient way, from which rectangle there is D. If I don't know if it's clearly visible, but it's D. It's M2, ins A, G. While the second one is from the hierarchy, but they are also flat. The sweep line is just memory. Classical structure, it's an interval tree. I want to be able to know which recognition for that. Find the root of the tile. We want to keep the graph tree. We want to keep, this is the canonical representation. And you have and maybe it's, so now, instead of making more slides, I hope to be able to make a live demonstration of how it works with expected, and the netlist is equal net. Second demonstration will be two wires that cross. The nightmare of any developer failure is a failure that appears only when the full hierarchy is assembled. That is, if you check level of hierarchy by level of hierarchy, you won't see top level above the standard cell of the netlist. There is something wrong in the standard cell, but something once, and it was a total nightmare. So, the first step, I use processor, the place and route correctly on the screen. So here is the placement made. It is n equal 1, n equal 1 of the cells. So here you have, so you have 13 equipotential, 13 routing paths. So here, because it's not selected. A bit deeper than the routing itself, you see get a transistor, so we get here the transistor, and here you also transistor as planned. C5, and I will break it. So, and now, that at the end of the routing, I will line on violet line means that I did break something. So the database see that we have unconnected things. I will perform the extraction again. 365. You see two. One with the first part, with one only, and the second part with the rest of the net. And you can compare easily with the netlist here when you debug. That's another point which is extremely important when you make a detailed router, is the ability to see what happens. Because if you just get numbers, manageable. So here, now the third case, a short circuit. So this time I will just create one short somewhere. So again, we will create the netlist, and we perform the routing again. Huh? I am accustomed to see always the same design. Okay, and we will look at the nets. So, sync potential, and I cheated because n equal 3, meaning that the nets in the netlist should be kept. See that the short is there. I added this net and this net, so you have two net shorts. So we have the third, all the third nets and selection. So you have. No, I will look. No, okay. No. Dimux 0, and we have this other net, which is the hold. So those are the two nets which are shorted. The most problematic one, what I did is that I put an error inside the standard cell. That is, you have an unclean standard cell, which generates problem at the upper design. Done. Now we can see the equipotential, which is a problem. So we can sync it. And the short is here because I know it. So what did happen? So if you look at the standard cell, is the metal 1 and here. Metal 2 is not connected to anything, so when you check your cell, it works perfectly. Maybe you will get a warning. The cell checker will maybe say you have some stray metal there, it can be a blockage or whatever, but it doesn't prevent the cell to work. But in the top level, when the root, we don't put a blockage, then it will short. You see it's there, and then we can have it. And we can, the hierarchical level, it's good. So, this.
As we are deeply short in time, one quick question. Yes.
On the layout, when you have VDD and then the location will get short. So I'm not sure if your software can handle this kind of.
Yes. In fact, it has been designed for that. I forgot that support. I can know exactly which rectangles makes the short. So it's not implemented in the locate, the geographical position of a totally very important concept on design. We must implement that.
Oh, great. Let's thank. All right. So I hand over the cable. He leads the novel computing technologies are on runtime, SI, and hardware security based on FPGA. Currently, high-performance computing and exascale computing, as well as reconfigurable instruction set extensions for CPUs and using FPGAs. And yes.
So thanks for the kind introduction, and that's on this year. If you want to attend, this is where we'll take everything started with getting and to basically explore memristor technology like the crossbar arrays on FPGA. Okay, so in order to do this, you know why I started building Fabulous. Okay. Well, there is already VPR out. The realistic research was Tyler. It does a lot of really important tasks to tweak it into the tool. Yeah, so if you say, I want to build a clone of a, let's say, Vertex 2 device, and you want to do this, and I know exactly I want to have a 100%, but if you have something like more, and a little bit of a control freak, so I wanted something new that allows me to do this. And one of the key philosophies is that we try to keep things tool, so models as we do this. Fundamentally, it does model generation. There's an easy way how you can specify a fabric, and then it generates you basically models that you need for the place and route tools. Because at the end of the day, you are not only doing the FPGA chip, you want to generate a bit stream that runs on that chip, right? So at that part that we have. Okay. Small quiz, what is this? Open source. Yeah, so open source is a key player in our project, and our ecosystem looks actually quite more complex. And I don't want to drive you through all the figures, we don't have time for that one. The only point I want to make is, for all the different, and we are kind of standing on the shoulders of giants, so we use like Joseph, which is the go-to place for synthesis in these days, ABC, we have Max here, so you get RAM blocks in these days. So there's really an open source ecosystem that you can build off, and that's what we did. Okay. Super tables. What is a lookup table? Just for an example, an AND gate, that's the Greek logic function. You may eventually want this on the data inputs. Yeah, and in front of the thing that's fundamentally different is that now the select inputs at the lookup table that are my data inputs, if you want so, and they select like a bit from the truth table. And the whole story here is an interesting one, because you only have to optimize very few building blocks to do a quite efficient fabric. Yeah, and this is all not new, so there was some work this was UBC, but Toronto did this also, that you say, okay, if you can just implement like multiplexes and let's just check your lookup tables, cluster cells, and eventually that is something that looks more similar like this one here. So if you specify that was routed, that you can then actually open in this editor, view it, and analyze it. And you get like some feedback about congestion and all the usual things. I want to drive you through a few details, but not entirely. You don't have to go through the entire table. There's only 6. I just analyzed roughly how many transistors it takes to implement a single logic block, which is in terms of the Xilinx vertex 6 down, how expensive is this to implement for the logic, how much does it need to do the configuration bits, okay? And from all these numbers, I'm only here in the bottom right, we take something like of them are tables. No, you buy switch matrix multiplexes. Yeah, so this is what you really buy. 80% of what you get from Xilinx. Careful if you implement an FPGA, and it should be efficient that you get the routing fabric right. This is actually more important than the logic. Okay, the FPGA is north of 1 gigabit of SRAM. Yeah, if you think about it, a gigabit of SRAM, 6 transistors per SRAM cell, we are talking about 6 billion transistors, at least for a data center FPGA to store just the configuration. We are not computing anything so far, it's just storing the configuration. Okay, so we are not the only ones doing FPGAs, and related in one long chain, and you shift it in, and this don't have a valid configuration, eventually short circuit, trigger bit lines, update, use partially configured value. A type packing in your fabric, and you adjust the width according to the wider, right? And you can check them out, get already, yeah, on adding this one, yeah, later, and what it does is, well, tiles, and what is a tile? It provides us some primitive. These, if you want, you can have hierarchies, but it's up to you to provide the configuration storage. It's just a simple text description. What's the begin name? What's the end name? It is a begin or end that is not so important. Yeah. Then that you throw in your own RTL code. You can just take our CLB, give it a different fabric, and inside your own accelerator, these bits and those stream at the end. Yeah. So, well, let's start with so all the outputs of the lookup table or of the switch matrix that are rows, okay, and all the inputs that are here. And in order to set a one, already switch off here at this point, as it's a very high level, and say, column in, you have already your custom fab with these things. So you can, but you do. Our first, that wasn't the first chip. The first one was a TMSC 180. This was the first Kai 130 chip, LUT5s as well. Blocks at the right, we have actually block RAMs. They are 1 kilobyte. You can program different aspect ratios for width and depth as we use those ones. Okay, like a small video running with this kind of street. And what this demo does is the image that you see in the background is actually stored inside block RAMs. We need a division for the scaling, which is done in logic. We use DSP blocks, so it's just to show that we can use all these different resources together and master that complexity. Okay. Another chip that we did that we couldn't bring up so far is this a T-shaped dual RISC-V system. So what you see in this chip photograph is in the top is that we take the operands that go usually from the fabric back into the register, okay? And we use some of the instructions formats that are dedicated for custom instructions in order to RISC-V cores can simultaneously. Unfortunately, that is not our fault to use, and in this infrastructure are hold time violations, which is not a problem of the fabric, but it prevents us to bring it up in full beauty. Okay, SoC to basic configuration. Okay, my hands. This one here is the first open from A to Z, including the, and if you compare this With the Shuttle 2, the tiles are a little bigger, but not much bigger. Yeah, so it gives you an impression that actually the open source tools are pretty close to what you can do with industry tools. So I'm quite excited to get this back on my desk. Was our first configuration storage here is not SRAM cells, use basically memristor cells. Yeah, and use a voltage divider. So I have 2 memristors for each memory bit, and one of the memristors will always be low, on low resistance. This draws a little bit more current, we know that, and this is why we haven't filled the chip, as we want to have a chance to bring it up without frying something instantaneously. Yeah, so it's tiny, but it should be just enough maybe that we can send out like a hello world message as a UART message or something like that. If you can really in memoristic states, which is pretty hard to read, we may get an advantage in density, which has to be proven, of course. Yeah, and another nice one is it's instantaneously on. Yeah, so if you can think of how fast your memory, that bridges almost that we did, deals with the I/O pads and so forth. If you do a hardware module, FPGA to bring it up, as Infosys, who is on this FPGA down here, yeah, but provide some advantages because we provide, let's say, your microcontroller, you can use them to store your code. Yeah, so it's one way to do this. And the way how we implemented this is that we just added a small FPGA fabric round about the size of this Caravelle, yeah, FPGA. And with left and right, we have connected user modules. Yeah, so multiple user modules got to be implemented on the same die. And we share basically the fabric, yeah. And this can be done, yeah, and we see that we have a bridge where you have it in. Yeah, and the beauty of that one is that the FPGA, of course, helps all the user designs. Yeah, and it could be in a different context each time because, well, you can reconfigure that. Proactive here. Oh, there is this project. I've never seen this working. If you saw this working, let me know. But in MPW2 in this Google Shuttle program, we both had a submission, and that was this open this demo that Myrtle did, is what I showed. And in that submission, and this is basically for to implement this. And traditional VPR approach, you have like tracks. I connect to the vertical tracks. I have artificial level of fragmentation because we can do it's more expensive. And since then, what's the trick there? Because we replace the full saving per multiplexer, then we might wear micrometers. And I don't want to drive optimization. And the message congestion was, this is the work in horizontal, the improvement, okay. So what we wanted to have is something like that, and what we actually got was congestion. So just replacing us the benefit we wanted to understand. Assume that configuration bit 0, and because the way it's connected, the 0, and it gets placed a little bit, causes actually more route, which configuration bit controls. The only thing that changes is that configuration bit 0, and if we do that, we get to a less congested routing. Okay, and this is what we did for this kind of scan chain approach, but we also you would have eventually your configuration latches. So the problem is nothing else as grid point mapping, yeah, and that has somebody solved this already for us. So you don't even have to do anything. If you just the figure optimization, and on the right is how it looks like after the optimization, and you just see visually that it's less busy, so it's much easier to route. Okay. That's basically my last slide. And it gets pretty neat in these days. So you can actually load your RTL code into that one, press a compile button, it triggers all the tools, and at the end you will see inside the editor your code after compilation. And you see right away the result here. Yeah, so things get pretty nicely integrated, and yes. I want to finish here. Just important thing to mention is this is a lot of work, also thanks to our sponsors, EPSRC and Carl Zeiss Stiftung. And watch out for There gave a lecture, yeah, and we will likely. So I'm Carl.
One quick question, one quick.
Do you understand what kind of support do you provide from the, let's say, from the point of view of the ASIC implementation? So you mentioned that you have some kind of complete in the complete.
You implement your file that you see there. This is what it fundamentally does.
Thank you, Dirk.
Okay.
Ask you, please stay in the poster section. So I suggest we watch. Thank you. The posters in the back. So thank you so much. Let me introduce you.
Just tell me what you want me to do.
Just need to connect and probably
Electronic engineer. He's been involved with open source silicon for the last 4 years and has sent 20 chips for manufacture. He has helped over 400 that has manufactured over 700 cube. Matt, welcome.
The room is, and I know you all want coffee. Who's just put your hand up if you've heard of Tiny Tape Out? Okay, so the rest of you can put your hand up now. Get wafers where we put lots of, and it basically is putting lots of little designs onto one MPW, so it even further reduces the cost. The smallest size we do is 160 by 100 microns, so that's about enough for 1,000 standard cells. And one of the key things that we're doing here is you can use this system with no tool download or install. So it works really well for a workshop or in an educational setting where the last thing you want to be dealing with is installing loads of tools. So we have this system, this is the latest version with a kind of central mux in the middle. We did a silicon bring up on a live stream, so that was fairly stressful, but I thought we're kind of pushing a lot of boundaries here by doing stuff with open source tools. So normally you don't get to know if a chip works first time, but we thought we would live stream it. So I think it was pretty slow, so we're running it at 10 megahertz for 2, and it does work. We've got sent it out to 150 people, and people are testing their designs. It's kind of amazing how quickly you can do with complete beginners. Okay, so the maximum designs that people did was like 2 or 3 standard cells, but then they could afterwards go away to drive the scan chain a lot for grades. We threw away the scan chain. That was like people are interested in it, so you concatenate tiles. So now you can, the biggest design you can do is about 20,000 standard cells. This was the demo design I mentioned. So this is the first one, control of the layout, so we're getting much better. About 20 nanosecond, the board's going to look like this. We now got a Raspberry Pi 2040 coprocessor on there, so you can plug it into the Tiny Tape Out Commander web app, choose a project. We can now support up to 50 megahertz. We can do. So there's 25 days left until tool chains that I'm learning mixed signal and analog myself. Nordic Semis. If you involved in a university and you want to just doing VLSI courses, should do a tape out. People, of course, Yosis HQ are the absolute fundamental bedrock of everything, thanks to Claire at the back. And if any of this is interesting, then please connect with me. I'm very happy to meet you. So thanks very much for your time and enjoy your coffee.
All right, so we restart the speakers. Make sure you are here. I think you.
What is the frame rate?
Then I have to.
Alright.
Then I have to check if we can see the slide. Perfect. Then Hello, hello. Hello, hello. Where is it? Ah, I have to select it here. Okay.
Ah, ich komme schon raus. Ja. Aber das schaut nicht gut aus.
Na?
Also habe ich eine zu hohe Auflösung. Was für eine Auflösung?
1920 mal 1080. Das hast du aber gerade.
20 mal 1080, das ist das Zeit.
Vielleicht alles drunter, ich weiß nicht. Das, die Framerate ist ein bisschen.
Ach so, wo stelle ich die Framerate rein?
So,
das ist nicht so nett. Aber ich kann auf jeden Fall die Auflösung runterstellen als Versuch. Das ist noch höher. So. Die nächste 16:9 Auflösung ist das dann.
besser.
Es ist aber immer noch, das war immer noch was. Aber das war jetzt was. Dann werden wir sehen. Ja. Ups. Okay.
Kontakt.
Das ist immer noch so ein Kontaktding.
Alright. May I please ask you to gradually return to your seats? Alright. So I hate to interrupt discussions, but at least for the second part of our talks, I would like that not I'm the one who is guilty for over-consuming time.
Don't introduce my topic because I'm talking about something completely different than what I announced in the program.
Yeah,
You need
you're always a good surprise. Surpriser. Okay, so for you, which I really doubt for me, to welcome HQ, a company focusing on phone hardware, numerous open source projects, including Yoast, Pico RE32, and OpenSCAD. 5-bit managed spec document. In December 2020, she was awarded the year's RISC-V Board of Directors Technical Leadership Award in enter active role in various other RISC-V technical groups. When she's not tinkering with RISC-V or open source EA, Claire is playing Go, Badook, Waikiki online, or is playing comically bad golf offline. So, without further ado, thanks for being here with us today. Welcome, Claire.
Thanks. So I'm talking about the users ecosystem over the course of maybe the next year. Some of them sooner, and some of them bigger things a little bit later. And the second thing that I will talk about, process like framework, where we have a shared database learned from over 10 years of your process development, IL++, where we list representation, because a lot of people, so there is some pressure with the RTLL++, and what are like simple things that we can do within it, and also allow. So it's an attempt of like a little while from the RTLL and traditional users side, so we then can actually do this transition to NGY and the integration of both of these universes. Okay, so let's talk about RTLL++ first. So the big change that we want to do essentially is we want to create should be compact. So the idea is that if you would want to annotate every cell in a design or every cell in the module, say with this entire ID space, and that is a very efficient way of then like adding additional things or properties to these design modules. And in most of the existing users passes, this is done using maps that essentially map a numeric representation, an integer representation of the name of something to the object itself. And with this, we can get rid of the name and the dynamic lookup, and instead of having a hash lookup, just jump to the right array index, which should speed up a lot of structure. And the nice thing about this is that we can actually add these integers in a way so it should not disturb any of the existing code. These units and destroying these kind of objects is something that is already done within the RTLL API functions. So there is no way actually for a pass to just like create a new cell without having to go over the existing infrastructure on the API that people would be using, just adding some additional API functions. And I think a very helpful like idea from programming and optimizing programs is this struct of arrays, and there are structs, but now you can annotate this with additional an additional struct of arrays where you have like individual arrays for the additional properties that you would want to add. Another thing that we would want to add are certain design level flags. If the main use case for those flags are the two that we have here on this slide. First is we would want to phases of the flow. We can set a flag, and then other passes that require the design to be in as such if the design is not like pre-processed enough. Because this is one of the most common support design where we didn't even run proc or hierarchy on yet. And that then leads to unexpected behavior. And actually it would be very easy for to tell if the design is in proper state yet. So to the design being elaborated, so essentially that means hierarchy and proc has been run. And probably we will create a new command of synthesis scripts that will, the default behavior of passes would be to require it. So we'll make this in a way that all existence passes will require that, and if they actually are intended to be run on passes, and external users who are programming against the RTLL API, if they write passes that are intended to be run that early in the flow, then they would also need to add a little one line or something like that to the C++ code for their pass, so that it will not reject being run on an unelaborated design. And the second thing is what we call here is a sample that maybe need to come up with a better name. But cells, where some of them represent memory input parts, and some of them represent memory write parts, and some of them represent memory read parts. A couple of like high-level or less wide parts to accumulate like all so having done this mapping step usually is something that like a lot of passes depend on. Then a lot of passes work best, let's put it this way, if there are no logic loops in your design. So in some cases it means that the algorithms might not actually terminate if they get stuck in a logic loop. In other cases it means maybe they error out, or maybe they don't perform the optimization instead of just give up because they see a logic loop. So we have a couple of things. The design, once it's in the is assembled state, each pass would actually be responsible to keeping these invariants in place, and we can check it between passes. The RGLL data format allows us to describe things like this. But for various reasons, it's useful to be able to at least read in such a netlist and then have different means where they might be used for like twisted outputs and things like that. But in the later stages of the flow, it's a little bit tiresome to have to write code in a way so that they can deal with these fringe, to be able to say, X for extensions that at any point in time. So here it's not like the design is going through a flow, and at one point we set the flag and then it's set for like until we are finished with everything. But this is something where we can change it and say, oh, I know I'm a pass who like doesn't want to have a certain extension active, then these flags could also be cleared again and these extensions would then be turned off again. Do I have an extra slide on some of this? Yeah, I've already talked too much about these two. One rules. So when you run optimization that is X aware, then you can propagate X's is X, even if it's just one. Then all the output bits X, even those output bits that technically would not be influenced by that input bit, because each input bit of the higher can only influence the output bit of like same weight, and then the ones that are like higher but not the ones that are lower. But that's not the way that the Verilog standard works. So very early in the flow we have like X aware const propagation that implements these Verilog rules. But then later in the flow we would want to do something like, say there are two adders and they use like the same input bits, but one of them I only need one input bit wire, then both of those are added, and both of those adders can be implemented by this one adder, and that's the pass. And it turns out that like the 7th or 8th input bit to this now like common adder that implements now both of the original adders, then we will erroneously propagate the X onto like both adder outputs or original adder outputs. The is assembled flag is being set. And once the is assembled flag is being set, we do not run this like high-level language-aware X propagation again, but now we run these optimizations passes that would do perform optimizations that are not preserving with respect to the Verilog X propagation rules. And this is also something where these optimizations all exist within users now, and there is of optimization on this sign are like additional options, but that's for most users not really too like obvious why it's common for so many flows using users that it makes sense to deal with these issues in a like more central infrastructure instead of just telling people, well, you should have written your pass right, or you should have written your script right, and if you just look at the manual page, it says even here, use this flag if you don't want to have this kind of X propagation. But of course, users usually are not aware of these kind of small issues. They just run their flow on a simple design and they see it works. And then they ship it to customers who then run it on more. So buffered normalized mode is something that should help us to deal with the current nightmare within users right now, which is like via aliasing. So when you've written users past, and you know there is this, or hopefully know that there is this sigmap thing that helps you to manage signal bits that are actually aliasing each other, and it will give you like a representative for each aliasing group of bits, and you might have like cell inputs that are then coming from different places. And buffers normalized mode is essentially a feature of a netlist where we, and in the cases where there are like concatenations, or where we would want to like only use some like slice in the middle of some like port bits, we get additional buffers added, and only the buffers are the one. So in your passes, you can have certain assumptions about like a port and its connectivity, but it also allows us to annotate every input port with a pointer essentially to the port that drives it. And that's not possible in general with RTLL, because an input port in general could be driven by a mix of output ports. So buffered normalized mode is our attempt at like dealing the design, wants the design to be in buffered normalized mode, and it might then just like call the appropriate command internally to first convert the netlist into this, check if the invariant that like is attached to it really holds for the design. And then we can narrow down where things happen. And this is, no, they're not here. Multiple inputs, and add one more integer again design. So whenever we update something, we like increment the global generation number, and we set the generation index for that one thing. We essentially have a way of telling index at generation, where I do not actually update things that NGY is written, that we would want, and then run certain optimizations whenever the optimization opportunity arises in the netlist naturally, where update function that will then apply the trivial optimizations we would want to be able to apply at every step throughout the flow. Our third is for keep maintaining a topologically sort order of the design, and then there is like a little feature here where we have an additional attribute that can then be used to pattern, but the loop should be broken. RTLL, and the hope is that we can NGY, but just using RTLL++, and maybe a little bit of additional helper code to like provide the kind of functions that. Oh, did this start at 5? Oh no. Okay, so NGY is the next thing. The idea is this already the first slide here? Interesting, yeah. So the idea is to integrate NGY with like the uses that we have now. So this passes and NGY passes, and whenever it's necessary, whenever you switch from like the one way around, so there will actually be an NGY executable, and that should also then like embed lib uses essentially, so that it can use the, and using uses is the NGY will then at each pass, after each point, convert back into stick in one form of the NGY database format. We used as is in memory. So we can just any pass or any read design that is stored to disk, we can just run an executable and be able to like extract the value or whatever from the design with almost the same speed as if you would like ask it with a tickle command or something in another, solve a couple of different problems. One of the problems that I'm hoping that this will fix, they say we can't give you like the input design, something like this. We can only try to like create a checkpoint at the end, and then you can get that netlist out. That's something slightly different when you write out the RTLL text file and then read it back into a new project, hit the same bug anymore. And what we want to do with this new binary database format is we want to make sure that all the state that we carry from one pass to the next is actually in that binary database format in a way that does not leave us with the same kind of issues that I have just described. And this is the reason this database is actually up to date with what, right in the middle of it, you will see the data look up what was like this recompile uses with additional print commands added, just so that you get like the kind of debug information that you need. So yeah, some of the high-level differences in the NGY database compared to what we have. Some people in the past that you can only select cells, but not can be able to select cell parts. And actually, when there are different drivers for the different slices that we have, so you might end up with like 2 cells of the same type, and the cell definition would say, oh, it has a data in. You would end up with 3 data in parts, each covering another slice, so that you can then have this thing that in similar for large output parts. If someone is like using only some bits of an output part, it can be overlapping, so that we can then get like easily the list of cells downstream that only use the are going away as its own types. Right now we use wires to like also implement the functionality of net labels. In the new format, net labels should become just a cell type that can sit on a connection somewhere and give it a name. And yeah, module inputs and module outputs. Module input part settings in the actual data. Structure is that it should be possible to add like so it behaves a little bit more like at runtime, and it will not break other stuff. And choose if the need increased, and we have to like move all the records. Also say this should be in a, can mix this, so you can have, but under the hood that different that we want to have is a dynamic cell library. So we have cell library, and if someone wants different cell types for their thing, we have already started, and this is something that we would want to that can deal with different flip-flop types. This you're mapping early to the flip-flop cells. Then also things like propagate constants. All these passes have like this long framework that we have. All these of cell types is not like, this is a thing that I want to do. Different customers who want to add our cell type, because most of the customer work that else, and they're implemented as a Yosus plugin.
Really like waveforms and analyzing them. From analysis language can act as a then the nice thing is this currently works, and the long-term goal is to have all directly in Surfer embedded so that it's even easier to use. But with what we have right now via the TCB backend, we can already do interesting stuff. Like you can, for example, inject new logic inside the waveform right inside Surfer. So you don't have signal that goes high whenever ready and valid are high. Or I have a system Verilog assertion to val compiler presented here at the poster. So you can write, or you could add a signal, a virtual signal I call them, that has is an abstraction for a bus, for example. So you can abstract your waveform signals. Then I have a different project. I want to be able to control the waveform viewer from outside. So we have a second TCP interface. It's not named right now, so it's confusing, but let's call it a remote control interface. So the idea is that you want to keep it simple, JSON commands that can add or remove signals. The stuff that Franz has shown, for example, like drawing things, highlighting things, going somewhere. And what I have in mind is a really tight integration of other EDA tools like System Verilog, check that maybe add new signal. It's not just for Surfer and Val. It might also be, nothing here is fixed. I think it would be very interesting to discuss this. Okay, that's for the extensibility part.
So, yeah, that's the extensibility part. There are more extensible parts if you want to do something cool with Surfer, let us know. Performance is something else. I think I added all the traces from my traces in the RISC-V. You have normal use cases. Surfer really saw me running this in the browser there. I've had several people actually tell me that they could open this website and just drag their VCD file in there, which was really nice to hear. we haven't implemented this yet, but I want to look at this for example, for it to fail, then you have to like download a waveform viewer or you server in other things. So we're teaching tools. So this is another thing that's an education tool where you can inspect what's there. And as part of this, we added Surfer there. So it's a use case for this embeddability. It's written in Rust. I'm a heavy Rust. Put maybe 2 hours. From library, we don't have to build up like 500, which is why I say perhaps too easy. It work. And gives us the data. Originally, so I finished that, and then I took his library. So I built the FST library. It does a lot. On a 7 GB file, we went as well because it compresses the data as it lines to your view. You should have the good program. You put it in one place, or like stores a message in the queue. Is exposed through this mouse or click a button. People have all contributed a lot. Surfer wouldn't exist. We've all contributed stuff to Surfer, which I'm very happy about. So in conclusion, I hope I'm still on time. Surfer is a snappy and extensible waveform viewer that runs pretty much everywhere. The extensibility, and here are a bunch of links. There's even a phone. So thank you.
Thank you so much, man. So, who wants to be the first one?
Who's on to start?
Sorry? No, I did take that.
Framework or you will need the
Then I wrapped this wrapped it.
Like in terms of waveforms, if I was something.
Gigabyte thing works fine. The one that took 6 seconds to load with the new thing, but I haven't actually benchmarked. Yeah, I don't want to claim too much.
Thanks again. At the end. Thank you for being issues in the beginning, for being here today. Thank you. Okay, and for those still being on YouTube, please don't forget to the bell.